electron withdrawing groups can be many different things. It could be carbonyl, just we talked about, or it could be nitrile, it could be other things. For the electron withdrawing groups, like the carbonyl, we expect Endo is going to be the major. But let me show you. Just one more time, we got the double bonds, the die inside here. And then double bond, I'm going to talk about what electron withdrawing groups going to be placed where. But they're going to, regardless what it is, they're going to come together and then make a cycle addition reactions. By pi electron comes out, making single bond here. That pi bonds comes in middle, double bonds move to the middle. And then that pi bonds comes out and make a single bond. So we're going to make a cyclohexene. And then these two substituents will be placed accordingly, right? That's kind of what the product's going to be. Just want to show that which position endo, which position exo. The molecule comes like this. These substituents is going to be land on the endo position down there. And then that one out of the ring, that's going to be end of the exo position. For the electron withdrawing groups, that has a pi electrons, like a carbonyl. It could be carbonyls of the ketone. It could be carbonyl of the ester. It could be carbonyl of the carboxylic acid. It could be carbonyl of the ester. There's so many variants, but as carbonyl, they have a pi bonds. We just talked about these pi bonds of electron withdrawing groups and the pi bonds of the diene. They kind of sticks together. So that's the reason why this electron withdrawing group with the pi bonds is right under the pi systems. So it becomes in the endo position. Endo position is a favor for the electron withdrawing groups that has a pi bonds. And then because of that arrangement, it's favored. These electron withdrawing groups end up being in the endo position, not in the exo position. And if we observe the same thing with the other electron withdrawing group, the pi system, something like the nitrile. Nitrile with the carbon, nitrogen triple bonds, clearly it is a pi system. And then when we test that, and we expect the same secondary interaction with the pi systems, and then this nitrile, we expect it to be in the endo position too. But there are other types of electron withdrawing groups we can use for the deals of the reactions, something like a trifluoromethane. Trifluoromethane is electron withdrawing groups because of free fluorine, full electron density out of the carbon. So that makes this carbon electrification. This electron withdrawing groups. But does the CF3 has a pi bond? No, it doesn't. There's no double bond. It's all single bond. So whatever the secondary interaction we are talking about with this type of electron withdrawing groups does not apply to this electron withdrawing group. That doesn't have a pi system. So they're not going to make a secondary interactions. So when CF3 bearing the double bond comes in, we may expect the same kind of a products be made, and that's endo position, that's exo position. Where the CF3 is going to go? It's going to go the same endo position, or it's going to go for the exo position. That's what I was trying to tell. This endo position is a favor with the electron withdrawing with the pi system. It's all because they can make a secondary interaction with the pi systems. But this one doesn't have a pi system. So coming underneath of the something very crowded is a really bad place for the CF3. So for the CF3, where that's going to be end up, they're going to be away from the pi system because that's technically more hindered. Once again, why this carbonyl goes to the more hindered side is because of secondary interaction with the pi system. It's kind of a special interaction between the pi system of the two components. This one doesn't have a pi system. So that's the reason it does not get there. So that's a prerogative. There's no reason to squeeze in there. If they have a CF3, it's a pi system, yes, that's what makes them go in there, but it doesn't. So that's why CF3 stays out being in the exo positions. So when they do the Diels-Alder reaction, CF3 is going to be end up being in the exo position. That's going to be the major product. So it's not like the endo is always a major product for all of the Diels-Alder reaction. You got to look at what's the electron withdrawing groups and nature of the electron withdrawing groups. If the electron withdrawing group pi system, endo makes sense because of the secondary overlap between the pi system of the two components. But if they don't have electron withdrawal, I mean, with a time system, then XL is actually going to be the major product. So I hope that this can clarify some of the confusion that you see